I hope. Okay. Okay, we are recording in progress. So let me go back to our screen. Okay. Oh, I have to admit, sorry. People, yeah, that's going to share. Yeah, okay. So let's start with Grover's algorithm. Welcome everyone to the session 5. I would call it session 5.1 because we had a session 5, but that was focused mainly on the IBM Qiskit. This time I'm going to change because Quiskit is still very complex to implement. We might see some other web browser-based options for people to drag and drop and just be done with it and save or not save and go ahead. And if you want to save, you can save. So that is what I want to take the approach today. A bit different. So the focus is on Grover's algorithm. So Grover's algorithm can be viewed in multiple ways. One way of looking at it is this way. That is, you have a what you call a bunch of boxes, let's say 8 boxes, and in one of the 8 boxes is what you are going to find what you are looking for, let's say. So I can represent or encode them as 3-bit operation or 3-bit as 000, classical I'm talking here. So 000, etc. up to 111. Those are the 8 combinations. Now, if we do that, then there is, how do you do the search normally? If it is unstructured and is unsorted, because if it is sorted, then you can get better. But if it is unsorted, because if it is sorted, then you can, oh, maybe I should go to the mid one, 4th one, and then see if it is matching. If not, it is less or more because it is in ascending order. So I can go then to 2 and then see. So basically, search can be organized in a sorted much easier than on a unsorted and unstructured. So if you're unstructured and unsorted, then how do you do? That is one. Second, even if it is a number, I have only limited to 8 numbers, right? But if it is a million, then the order of, if I am doing unsorted, then I have to do million operations to be able to locate it. But if I use a quantum algorithm, like example, using Grover's algorithm with a advantage, it should give some advantage. Otherwise, why do we use Grover's algorithm? So it gives approximately a quadratic advantage, they say, which is nothing but if you have n elements, then root n. At least you can, if you have a million elements and you have to search for something, it's like searching something in the haystack types. So if you have a million elements, and then you are trying to get one of them, then you have to give at least 1,000 operations. So the best you can get is quadratic, and quadratic is nothing but root of n. So if you take a 10 raised to 6 and you do a square root of that, that gives you 10 to the power 3. So you have to, so the order is, they call it big O notation, how complex it is. So we say O of the order of root of n. Normally, the standard, if you do unstructured, you get O of n, which is, if you have a million, you have to do the worst cases, you have to search all the million boxes to figure out. So we are talking of 8 boxes here, and we are talking of 3 bits encoding. And so now the question is, how do we go about it? So one way is, how do we know what is the one we are looking for? So there are a couple of formulas which are important, and those formulas generally drive it. And here what we do is, suppose we have a, let's say kit A, because this is kit 00, kit 01, kit 0, kit 11. We have got 00 to kit 11 because all we do is vector representation. So instead of binary being encoded, that is representative of the kit notation. So kit 000, kit 001, and so let us call it kit A as a generic term. So if you have a kit A, now if you have 8 of them, then you have to have all superposition of all of them. So one way to look at is superposition all of them and you create a vector, and that vector we call it as phi. So phi is a superposition of all the 8 boxes represented in coding terms, and if you get that, that is the superposition of all. Out of the superposition of all, only one, which is ket A, is your target. So you have ket A, ket B, ket C, that means ket 0, 0 to ket 1, 1. All of them are superposition together to create a phi, which is all superposed vector, which is 1, and the other is the victory or the target. So you can have A as the target and phi as the superposition of all. Then if you take what you call rotate your phi, now A and corresponding to A, we are talking in 2 dimension here, so which is equivalent of because we have a vector space, so there is a difference between representation in 3 dimension versus 2 dimension. We are talking of Hilbert space, which is virtual space, and in this case we are talking about a vector in 2 dimension, and since we are n is equal to 8, it is 2 to the power 3. That means we will need at least 3 qubits to represent the 8. So when we encoded, we said it is 0, 0 to 0. So we have got right now 3 vectors because if you say psi equal to some linear combination of all possible combination, and in our case we have n boxes which is equal to 8 and which is equivalent to 2 to the power 3, so we will need minimum 3 qubits. Let's say A, B, C. Okay, simplify it. So A is our target. Just say A is the target and B, C are unknown. They are not the targets, but they are part of the search space. So you got A, B, C search space, of which A is the target and B and C also are there. So when you combine A, B, C superposed together, we create a vector space of 2 to Hilbert space 2 into Hilbert space 2 into Hilbert space 2, which is complex 2 into complex 2 into complex 2, which is 8. 2, 4, 8. 2 into 2 into 2. So we have got a Hilbert space of 8 dimension, and in that 8 dimension, it's a virtual, in the sense that you can have a number which is combination of real and imaginary number. So part of the component is real. If you take one variable, one parameter, or one of the numbers, that number is a complex number. So it has a real part of it and imaginary part of it. So we can say A plus IB or whatever, A plus JB, whatever you want to call it. So that means you have got 2 variables in that. Now, when we take a superposition phi, which is nothing A, B, C, that is you are taking a alpha, beta, gamma, delta kind of thing, right? So that means you have coefficients. So each coefficients you are talking of them all are superposed. So ket A plus ket B plus ket C, that is not the plus, but the cross. We have to take a tensor product of it. In quantum, every operation is a tensor product. So if I say A, B, C, I have ket A, tensor product ket B, tensor product ket C, and that is all that we have right now, and which is equal to phi. So our vector phi is superposition of all possible search space combinations. And then if we take one of them, suppose assume that A is the vector. Okay, A is our target. If I take a perpendicular of it, which is nothing but orthonormal or orthogonal, whatever, both together, that is A perpendicular. So A perpendicular is at 90 degree to it, because we are in 2-dimensional vector space. Don't get into what do you call the Q sphere, because we don't want to we want to keep it simple, so it is vector. So A perpendicular is nothing but this. So if we swing our whatever the angle phi is with respect to A perpendicular, if that is assumed to be theta, then you take the superposed combination, which is tensor product of ABC, and rotate it around the A perpendicular. Do we know A? Do we know A perpendicular? No. This is assuming that if this is the way it is, then you will be able to get a theta around, because you have this angle is theta, this will become 2 theta. Now so this is called vector V. A vector V is a rotation around the A perpendicular by whatever angle it has, which is theta. So it will go theta. So it will go 2 theta, because you are swinging around this. So you are rotating this and you are getting a V. And now you find that with respect to the superposition of all the angle is 2 theta. So you would like to swing this around the superposed all of this, which will give you WV. Now we can look this in a very different way, just to give you a picture in a different way. I will show you. But so we have moved it WV. So WV is nothing, a combination whereby you are getting closer to A. If I do one more swing around this, then I'll get 2 more theta, because it will become 2 plus 2, 4 theta. Then I'll move this 4 theta. So every rotation WV, which is nothing but a transformation. So you do a V transform, which is a rotation. You do a W transform, which is a rotation. If you do VW 2 times, then it will become closest. That means your average, we will show that average, but basically your angle approaches closer to A. At some point of time, the probability that it has hit the A is high. Therefore, all other get diffused. Only the one which is target gets a victory in this case. So this is in terms of angle I showed you. Now, in terms of what you call implementation, so what happens here is you've got a n qubits, which is nothing but in this case A, B, C, we said 3. You take a Hadamard of each one of them. So that is why we put n. If it is 3, then you will have all 3 must be Hadamard. So why do we do Hadamard? Hadamard is done for superposition. So if you have qubits 1, 2, 3 or 0, 1, 2, and you want to do a superposition, do you apply Hadamard to each of them? You will get a kind of so basically you get into if it is a 0, you get a 0, 1. So essentially what we do is whatever input you give, you are trying to bring them in a XY. So normally when you do a X, you rotate around X. When you do a Y operation, you rotate around Y. When you do a Z operation, you rotate around Z. Whereas when you do H operation, you do a operation whereby it goes 45 degree in the space. If you look at the block sphere in terms of block sphere, then it is in the 45 degree angle of each other. So in Cartesian coordinate, if you look at it, it will be 45 degree between the vertical and the horizontal. So you can get a cos component on the horizontal and the sine component on the vertical. So essentially our goal here is to rotate and rotate in 2 dimension. Although I described about 3 dimension, here the goal is, because it is imaginary, right? It's virtual space. Unfortunately, you cannot see the virtual space in 2 dimension, and especially if you got 2 into 2 into 8 dimension. So all we are saying is, hey, I am thinking I am in the space which is looks like a XY coordinate simple surface, and then I'm just rotating V, rotating W. So you repeat VW n times, and you need to rotate for this is the formula, let's say Grover's formula. If you repeat pi by 4 into root n times, you should get the result. So if n is 8, if I take a root of 8, that will be 2 root 2. So if it will come as pi by root 2, because you have got 8, you got 4 here. So it will be root of 8 is 2 root 2, because you are getting 4 into 2. So 2 by 2 and 4 you will get cancelled. You will get a 2 at the pi by 2 into root 2. Pi by 2, pi by is 3.1, let's say 3.1, and divide by 2, that will be 1.5 or something, and multiplied by root of 2, 1.4. So 1.5 into 1.4, so it will come around 2 times max. So basically, if you have 8, you are gaining, what we are getting, a quadratic gain. That's what we are saying. If you have 8 number, the worst case will be how much? It will be 8 times if you do in a classical way. If you do a quadratic way, which is a Grover's algorithm way with a VW operation, then you will do 2 operation, and within 2 operation. So there is a gain of quadratic. So instead of 8 operation, you will do 2 operation to get it out. So that means it proves that there is a quadratic advantage. And this is in terms of circuits. You can call it as Oracle here, because black box approach it is. So you have a black box with some function, we have a black box with some function, and we are just taking a Hadamard and taking a repeat operation, and we get the output. Now to measure the output, of course, we will do some either a Hadamard, or you may just put it on the qubit to see in the Q sphere and all that. So what I want to do is I want to use a alternate approach. So basic search, you are trying to optimize, and you are going to get a quadratic advantage, no more than quadratic. Even though we say, oh, we'll get exponential gain, that's not true. The best case, even in classical, they cannot get better than quadratic. And with lesser operation, we can get lesser operation in terms of use of computer resource. Okay, but to build the encode the data and all, we may take offline time, but that does not consume the what you call the resources for computing. So now what I am going to do is I am going to take a different approach, even though it looks odd, but I would prefer that. So there is some algacert.com quirk. So what I'm going to do is I'm going to go to what is it? Okay, let me just say whether I can get this. Oh, of course, you will not see it until I show it, right? So wait a minute. So I'm going to go to okay, let me just type it out. https://algorithm.com. Okay. So let me share the screen now. I want to. This is a bit different, but it's better be different than using the same thing. So where is my share? Okay. No, not resume share. I want to reshare. So I have to stop share. Okay, I have to stop share. And now I am going to share a new screen. And this time I am going to hopefully get this share. Yeah, okay, where is that share again? Yeah, let me get this. Yeah, I think I'm going to, yeah, I'm going to this share. Okay, so can you see the new share now?
Yes.
Yeah, I think you have seen. So this is a better way. So what you do is I will type into your chat window. Okay, and this is what I want to give to everybody. https colon slash alga sscrt.com slash QUIRK. Okay. So can you have you got this link? https://algassert.com/quirk. Okay. So this is the one I would recommend. There is a grower because it's an algorithm. We want to make sure we can cover as much of as we can. So your growers, your shores, these are the two primary. If you do these two, uh, more functions than composer. What is it? Some question is there? More, yes, more functional than composer. Yeah, of course. So what composer is? IBM Qiskit. We saw composer last time. So what here the contention is that this is more. Yes, it has got around 12 qubits. So IBM Qiskit, if we do of course we can choose better, but for us more, 12 qubits is more than enough for most of our operations. So you can try out any of this. How to use it, there is a whole thing. There is a tutorial you can run, but I will just get to show you the just a simple operation so that you can go ahead and create all that is possible. So then what will hurt you is not knowing the algorithm. You are better off if you know the tool, you don't know the what you call algorithm, then you can always learn the algorithm and apply on the tool. So trying to become an expert in Quiskit is a little harder because you have a lot of resources required, but this is a very simple one. Just it's over the web. Not only that, you can save custom gates, whatever you create, plus you have got the bunch of the gates, which is most important. Is obviously we are going to look at XYZ. This is X, even though it is written plus because that is the symbol used on the gates. So you can drag and put them in. So example, I'll take, before I do all that, let me take the chance and put it here, and then take this all across. Okay. So we have got something where right now we have got 3 qubits. Okay. 0 qubit, it's showing 100%. So you can look at the chances. It is currently 000 and it is 100% at this time. Whereas if you take here, this is 0011 and this is at 0%, and so on and so forth. So 111. So because you know that if you have got 3 qubits, what will you get? You get 111 as the largest and 000 as the smallest. And that means abstract. To put it, it's an abstraction. So ket 00, you know that if you have a tensor product of two kets, that is, let's say ket A, ket B. If ket A is alpha 1, ket 0 plus alpha 2, ket 1, and let's say B, ket B is equal to alpha 1 prime, ket 0 plus alpha 2 prime, ket 1. So those are the two. If you do a cross, if you do a not cross, if you do a tensor product, then you will get into ket 00, ket A will become, so ket A, ket B were separate. Now it will become, when you do a tensor product, it will ket AB, ket AA, ket AB, ket BA, ket BB. So basically, that's abstraction, right? Instead of that, you can even play with 00. So if you have 3 and you do a tensor product of the 3, you are going to get ket 00, ket 01, ket 0. So you can see that you can list ket 00, ket 01, ket 0, 10, 11. So basically, oh, there are people in the waiting room. Okay. So, sorry, let me just admit all of them. Oh gosh, what happened? What happened? Did I get? Okay, admit all. Then what happened? Am I out of this? scenario. I'm sorry. Are you able to see my screen now? I think we again I lost my what I was doing here. Very bad. This is okay. Okay, let me come back again. Hopefully, I should be able to get in now. Yeah. Yeah. Admit. Yeah, looks like I lost my. It's still connecting from my. Yeah. Okay. Got it.
Got it.
So
Now what I need to do is,
yeah,
I need to share the screen.
No.
Share the screen.
Oh, okay.
I have to make the host. Change the host. This is weird. So make host. Yes. Okay. So now I should be able to. Okay. Again the. Okay. So let me go to Chrome tab and. Okay. Share the screen. Sorry. Yeah. Okay.
So we are back to the shared screen.
Yes.
Good.
So again, this is a weird stuff. Okay. So what I was explaining. What's the problem here?
Yeah. Can you hear me now?
You're on double mics there.
Oh, I'm in double. So where am I in double? Bit confused here.
So I'm in double.
I know I'm in double is okay. But I am in triple, that is problem.
You just have to turn one of your mics.
Okay. I got it. I got it.
I will do.
I will do this one. I will
Mute. Okay, we should be okay now?
Yes.
Yeah, okay. Sorry for that. So I got disrupted and in the process of admitting people, and that, I don't know, I have to clean that. How to, that's why I prefer to use Geo, the other one which I use for the other. I don't get into this mess. Okay. Now, man. So you are sharing screen. Yes, I'm sharing screen. So what we saw here that we spoke about grower search algorithm. We talked about the 8 boxes, and therefore we have ABC. And when we do a tensor product ABC, we get nothing but instead of ABC, I call it 0, 0, 0, 0, 0, 0 being the 100% of it, 0, 0, 1, 0. It's and then the last one we talked about is 1, 1, 1. So this is how we have 3 qubits. Now the question is, how do we do some operation? Let's just start with simple operation that I want to do a Hadamard of this, and then you can see here what happens. So 50% of the probability has come because of the Hadamard, because now the K 0, 0 is now pointing in a different direction. This is the representation that you have 50% of decimal 0 and 50% of decimal 1. What it means is we have, so you know that we represent in quantum a qubit as a linear combination of the basis vectors. Those basis vectors being 0 and 1, and so ket 0 and ket 1. So the Hadamard, when you apply, it creates a on a qubit. When you apply Hadamard, it becomes 50-50 probability that it could be 0, it could be 1, and that probability is represented by this. And in the terms of block sphere, which is nothing but a XYZ direction, it is represented as rotation around, in this case it is rotation around the axis which is going between z and x, z and y, because you are on the surface, a vertical surface. You are rotating around the vertical, around the x-axis. Basically, if you are moving, so basis, there is something called as standard basis. Standard basis is always going to be 0 or 1. But if you are going to be a non-standard, or in that case you say alternate basis, the alternate basis can be, so if you have x, y, z, 3 direction, the alternate basis, example, just based on 3 directions, it could be, instead of doing on, normally what happens when you say standard basis, it reflects that you have x, so in horizontal direction something, and in the horizontal direction whatever you see, that is your 1 0. That is, you represent a ket 0 by a column vector which is 1 in the first row and 0 in the second row. So column vector 1 0 represents ket 0. Whereas if you do a spin, this is also called spin up, which is standard basis. If you do a spin down, then that is equal to representation in the 0 as the first row and 1 as the, so 0 1 in the column matrix. So ket 0 and ket 1 are nothing but spin up and spin down, and when you do a representation, you say this is a probability, and this is ideal case. Okay, you, if you do actual physical implementation, that may not be ideally 50%. It may be 49.8 here and maybe 51 point there, because there is a noise. Here there is no noise, we are just simulating, so you get 50-50. Okay, so if I put a Hadamard on the second one, the same thing should happen. So let's put another Hadamard here. So you will see the second one also, qubit has become a probability that it is 50-50. Then if I take another Hadamard, let's say, and put it here. So what we have done is, we have combined all of them. So basically each one is now a linear combination. And then what we can do is, we can bring together all of this by, let's say, putting a x here, and then we can bring this here, control, and then have this. Then similarly we can put a plus here, let's say another one here, and then we can bring here. So now what has happened, everything is combined. So essentially what we have done is, we have done a linear combination of all the Hadamards to get to a position where all of these are 50-50-50. So basically this is equivalent to your superposition of all the gates, all the qubits. So 3 qubits, all of them superposed at this time. This is the equivalent of our psi. If you remember, in our slide we said psi equal to combination of ket A, ket B, ket C, or we can call it ket 0 0 0 to ket 0 1 1 1. So this is nothing but ket 0 is nothing, initialization is 0. Okay, but these are 3 qubits initialized to 0. Hadamard been applied to make that it is a linear combination, and a control not being applied to both of them to combine all of this to produce the equivalent of your superimposition of all qubits. So this is the first requirement, because in the case of Grover's, we said that we have to get all combination first. First is superposition. Now after putting the superposition, we have to know, I don't know what is going to happen. We are just going to do operation like this, WV operation, as we mentioned. Now we don't have the oracle or here, which is WV combination. So what I'll do is, so at least you understand now how you can create. And you can also, if you want this, you can save this also, or you can export it, and you can have all this. You can look at the JSON version of it, JSON version is simpler. So you are doing a 3 Hadamard followed by 2 X's, and this is what it is. So you can use JSON from the copy end, or you can use the this link to show to everybody, hey, this is the link where I have everything, right? So this is how one can provide what you call the application. Going back to, let me go back. So I was here on this link. I hope I can go back. No, it goes out of, gosh, it went to Google. Okay, never mind. So at least I have shown you what you can see on a what you can do with the creation of the gates, the superposition of the gates, and to apply the Grover's algorithm. Obviously, you will have much higher difficulty level, but as a at the primary level, what I want is Quiskit may be very complex for you to handle, so you can use this web-based directly, try out all the combination that are possible on that. And we know that here, I'll just go back to https:// what is that? Algert, right? Algacert. Okay, so we are back again to our Algacert. You can see it on the screen, and here there is a Grover's search algorithm. Okay, so the complexity of building the circuits you can see here. Okay, all I am trying to say is you need a Oracle. Oracle is a black box, so you need a W operation to rotate around the superposed, which is what we saw right now. So we only did this operation, and we did for 3 only, whereas here there are more than 3. So okay, first thing you remember, one principal thing to remember is if you have a classical implementation, the classical implementation requires 10 gates for a Grover's for the 3 qubit. Okay, but then, so you can call it as x1, x2, x3, x10. I'll just assume that x is a gate, x1, x2, x3. So you require 10 gates to complete it. And those 10 gates have to be what you call repeated. That becomes one oracle. And this oracle, this oracle, this oracle. So W operation, V operation, W operation, V operation. And then you come to, we said that for 8, you need pi by 4 into root n, and which is root 8. And then we arrived at a number approximate 2. Approximated 2 rotation of WV we should apply. So here we have done by applying Hadamard to all of these, you get a superposition. And when you get a superposition of all possible combination, then you apply the WV operations. So W operation, V operation, W operation, V, and finally you get to the number which you want. So this is what is a application of gates. We may not have all the time in the world to right now show, but I wanted to make sure that you understand that rotation is the only thing we are doing. And so abstraction wise, we have got 8000 to 111, which is 8. And all those 8 we have fitted into 3 qubits, but because you need ancillary qubits. What does ancillary qubit mean? Like example, if you do a classical search and you want to find the greater than A greater than B, then you will take a C, buffer C, where you will try to A and B you compare, and then you rotate between A, B, and C. So basically result has to come out somewhere. So for result, you will get some A and B comparison result is in C. So you need one more buffer. But that is possible in classical because you can afford to have any input, any number of output. But in quantum, if you have n input, then you must have n output. So if I have 3 qubits and I am trying to solve a problem where I am going to get additionally some more input and output, or some more output, So then I need those additional qubits to store them because there is no memory. So what is it? Could you open? I'm sorry. Could you open quantum teleportation? Could you open? So you want me to explain teleportation?
No,
Kevin?
just like this demo, it does something different. I have a
Oh,
question
okay.
about.
So you want me to open a different in the menu? Okay, I'll go ahead. I'll show you. Billy, this one, Billy.
Quantum teleportation.
Oh, okay. So, okay.
See, it's
Maybe
spinning.
Kevin, go ahead, explain this teleportation so that people can really grasp.
Well, my question is the spinning. I saw this feature and I don't see this in Qiskit.
Mhm.
Is this like an active circuit? Like it's not a dynamic circuit, but like the qubits.
Oh, okay. So you have
continuously-
at the bottom, there are some function of T.
No, actually at the top it says spinning in the yellow, ZT's in the yellow.
Oh, okay.
So
This
you can
one?
add a spinning gate, and this is what I was kind of thinking because quantum circuits seem like you're just optimizing angles and you're just sitting. Like what
Right.
exactly is spinning doing in this demo?
So, okay. So because it is at a given time, you don't know exactly what the state is. It is dynamic, right? Because it is probabilistic, so it will keep on doing some random stuff. So your probabilities will keep changing, right? It's not going to be same constant all the time.
So you constantly want to change the rotation of the qubit.
No, it is by nature, right? By nature, it's some probability. It could be 49, 59, 51, 53. So we don't know where it is and how it is. It is constantly evolve. So, okay. First thing is in teleporting, we do entanglement. We are trying to entangle and then that entangle we want to teleport, right? That's what is the phenomena here. So the entanglement means what? You can be at 0, you can be at 1, you can be a combination thereof. So the entanglement needs to be teleported as is. Because if you try to break a circuit or reset a circuit, reset is a costly affair in quantum. If you reset, then you cannot get back what you want. Whereas if you entangle and teleport, then you don't have to clone, but you've got the ability to transform from one state to another. So 0-1 presentation to 1-0 or apply a Hadamard to get back the state. Right? That's what Alice and Bob do when they transmit. They take from a single source, you take both the what you call the states. You absorb a state from a single source, and both of them carry with them. One is here, other is on the moon, and yet they are able to instantaneously. If one, you can't clone, right? But if you try to do a what you call the measurement, then it collapses. But the other end, the spooky end, we call it, that should also collapse to the same state. However, you don't know what basis I measured and what basis Alice measured and what basis Bob measured, but they will retain the state. And that is important before collapsing.
Well, I guess just for the spinning qubit, is there another term for that, like continual rotation of angles?
No. So this is time factor, time basis. Dynamic, they call it. So you see at the bottom, there are this has got really superb. I think I will get this presented in a better way. I just wanted to share with you that you don't have to use Quiskit. This is a fantastic one, and this was presented at by NASA folks from in the Seattle event where I went, and I was really impressed with this tool. Last time I don't remember having seen this school. 2 years back, I had attended the Quantum Week. I had not seen this, and this is coming out. And this is some cool dude. I don't know, some college, some
Well, the
high
other
school
thing
student did this.
is the whole circuit appears to be saved in the HTML, the
No,
link.
what you can do is you can save this as a custom gate. So you can see custom gate here, right? Messages received. You can you can save this here. You can drag and drop this here. So basically, I can create an oracle of, let's say, example for Grover, or for QFT, or for, let's say, for other one, what is that? Growers and what is the other one? Research, and then for factoring.
Uh-huh.
So,
The only thing I can't find save as an image, like save as a PNG.
I don't know what they do, but this toolbox appears to be a great one. No, you can't get you can only save the session and recall the session back. That means you can save it as an oracle here. Like example, if I do a quantum Fourier transform QFT, I can create a QFT and then save the QFT. And then I know that I can apply a QFT to any algorithm. And then so I can take that and pull that into the boxes and then use it. So this is a excellent, cool tool. I think at this time, I don't want to get into details. Only thing I wanted to share was Grover's algorithm, and then quantum Fourier transform, and then what do you call the, what is that factoring algorithm? I tried to remember the name. Another algorithm which is here, I think we can go to the menu and see that. So Grover search, then quantum Fourier transform, then you got Shor's. So Shor's algorithm is prime factor determination, right? So if you have a number PQ, and if you do P into Q, you can, P and Q are, let's say, prime number, and if you do multiply P and Q, you get some number, a prime number, let's say, call it as A. So if you multiply P and Q, get A, but if A is large, okay, let's say billion, 1 billion and some number, how do we know that 1 billionth number, whatever we are saying, has a prime factoring PQ? Is it available? So there is a whole bunch of theory on that. You can go through trying to do a greatest common divider, getting a GCD, and then trying to bring out of it. So basically, all algorithms require some experimentation, and it is not like given that you can take, as I said, you can take any classical circuit and convert it into quantum circuit by adding enough additional qubits so that it becomes reversible. One aspect. Second, not only it should be reversible, any intermediate results that are produced have to be uncomputed. So there is a computing part. So whenever you find a circuit using all this, you will find there is a half part which you try to arrive at the result. Once you have arrived at the result, you needed, let's say, 10 qubit to do a job of 3 qubit, then those 7 qubit have to be uncomputed. That means they have to be brought back to original state. So not only reversibility, uncomputing. So you can take any classical gate and convert into quantum, provided you are able to do reversibility apply on it by doing uncomputing after computing the result. So they will always be symmetric. In the sense, first half part is for computing, next half part is for uncomputing, and you will get the result. The reason why uncomputing is needed is because you have to zero out or you have to null out. Because if you give a 0 as input, and if you need to get 1 as output, and if you give 1 as, again, if you give on the same gates a 0 as input, the other side it should come as 1 as input. That means those 3 plus 7 must be computed and uncomputed. The 3 will be real participant of the computation, and end result will be 10 in and 10 out. So you can again go back, reverse it, 10 in and 10 out. So what it means is you have reversibility, you have compute, uncompute, and you have differentiation. Like in Grover search, the idea was, if you take, suppose, 3 qubits and you have a mean value of that, the mean value at the initially is, everybody is, say in this case 8, so you are going to get 12.5% of each. 12.5 into 8, that will be equal to 100%. So that means you will get 12.5% as average. But assume that one of the inputs, which is your input, is negated, which is the target, which is based on the circuit. So because you are not going to give 0, 0, 0, 0, you initialize 0, 0, that is one thing, that is separate. But when your input is real input, which is one of the being the candidate, then that particular will be negated. That means you will get one flipped, one of them flipped. So out of the 8, one gets flipped, that is one goes negative, then average will come down. The mean was suppose 12.5, now it will become maybe instead of 12.5, it will become maybe 1 less. So it will be 11.5. So 11.5 for 7, 11.5 minus for the other. Now if you go one more round of them, then it will become 11.5 will go to 22, whereas these guys will all be coming down, mean will come down. So you are trying to diffuse in a way that your required target becomes higher and higher probable. And when it reaches 80, 90%, then you have the solution. At least you know that approximate, it's all approximation at the end of the day, right? Quantum is approximation computing. It is not real exact. It can be exact, okay? It's not that it cannot, but in general, it is an approximation. Instead of using numerical analysis and all that, you are doing here an approximation using the state vectors and state basis. So QFT, yeah, QFT is simple. I'll explain you. It is nothing but it creates a. So normally Fourier transform, what do? You do a time domain to frequency domain. So if you give an input in time, it will produce a frequency, and that frequency is nothing but sinusoidal sum of sine and cos. So basically it's a Fourier series, right? But it is discrete. First thing is there is a difference between analog, what you call continuous domain, where we talk about Gaussian noise and all that, which is continuous. Normally you do a what you call a distribution, normal distribution, where you get a variance of the results, which could be between like a what you call asymptotically going up and down, right? So essentially you are looking at let me just see if I have here. So this is the quantum Fourier transform circuit. Now what I want to say is you can have any circuit, but it will go up and down. Whatever you try to create, you have to undo it. So this in the case of quantum Fourier transform, what you need is the ability to separate out the terms, cost terms and the sign terms, and you should be able to either be able to what you call cancel, or you should be able to enhance. So either you have, suppose you have, example I'll give you, okay? For the QFT, the simplest example is a circle with a unity, and let's say we divide it into 12 partitions. Each one of them is 30 degrees. So 360 degrees covered now. So when I move a vector 30 degree, then what happens is you get one position. If I rotate 12 times, you will get back to 0. Because, so that means what? Omega, which is the angle, and if I have omega 1, 2, 3, 4, 5, 6, omega 12, after omega 0, if I take omega 0 to omega 11, that is my 30 degree rotation. At the end of the rotation, I'll come back to the same. So basically what it means is a periodicity. So every 30 degree, there is a periodicity where one of them is the enhancing component. So if you draw arrow going out, then what will happen? Arrows all around, flying around, will cancel each other. So one arrow at 30 degree going in the what you call first quadrant, corresponding to that in the third quadrant will be in the other direction. So they will cancel each other. So essentially, the quantum Fourier transform exploits the discreteness of the angular movement, and that angular movement ultimately boils down to only you will get either a odd or a sum of odd component or sum of even component. So whatever that summation comes out, discretely I am saying, because you are doing sampling, and that is what matters in the quantum. We'll discuss about it next time, but I can, what we'll do is, this I would like to see if we can have some of you demonstrate. If you go through this and try to, each one of you try to do some demo, then you will have a better idea. Then I'll explain easily what the various algorithms are. So our algorithm next week, what we'll try to do is use this tool to be able to grasp the dynamic. So one is the time factor, because every time, so we say in quantum, it's time and the space. So it's a time and space uncertainty. That is what happens. So if you try to measure a parameters in time, like electron is spinning, you don't know what position it is. If you know the position more accurately, then you are losing on the what you call the movement of it. That is the dynamics of kinetic portion of it. So it is all energy based.
Can I throw something out there? Just looking, I like that gate because it's interesting. I'm trying to figure as it changes its perspective based upon each gate. The results are for error correction. So we can take error correction and do what we need to do based upon this particular model.
That's right. So
Okay.
John, this is John, right?
Yes.
John, yeah, exactly. So error correction is not here, but actually you can get results. That's the key. We can always add error correction in any of our circuits by applying. So error correction, and that's a major play in the game.
Well, that's always been, since I took the first class, that was always been my big thing. Yeah, as you increase the amount of qubits, essentially, and I don't want to go anywhere past a certain point, but how are you assured of the actual final result? You know what I mean?
So
that snapshot shows you, and how accurate is, say, 2, 3, 5, 10, and then we'll stop at 10, and I'm not going to.
So
I don't
the term
understand
used
everything.
is called fidelity. So you try to get the fidelity higher and higher. The more the number of qubits you add, your fidelity will go down, and that is where the challenge is, how to reduce per operation the minimization of the error either through feedback or whatever means. So there are many means to overcome the error problem, and that is minimization of error per unit is important. So
Well, no, it's just to me, it's just getting a feel for building these, and then basic understanding, understanding what error correction is along each path. It's like building a circuit. I mean, building a program. The understanding as I play around with this stuff and get deeper and deeper in it, build security in first, and then you worry about all the stuff that comes along. You don't build it in a second. It's all planned ahead of schedule. And as you expand your knowledge and experience through practice, essentially then that becomes a more area subject matter. Is that making sense? Make sense?
Yeah. So maybe Kevin, you can answer him. Yeah, he's
Well, I had questions myself.
okay.
Like just
Go ahead.
breaking this down, like simply, like you have 8 qubits. So as this green line horizontal on the left goes down, it's just running the first qubit. It's just running the second qubit all the way down to the last. And then the outputs are frequencies, right?
Correct. So interpretation wise, yes. So what is the end of the, it is nothing but trying to get a frequency from time, right? QFT is nothing but it's a transform time domain. So time samples are there, and it is trying to get a frequency corresponding to that. And these are so at the side you can see the frequencies keep changing as the time passes through. So we call it as shots, right? In Quiskit we say that we take a 1 shot, 1,000 shots. So this is the shots. It can take n shots, and you can get, here we are not taking many a shot. We are just going through qubit by qubit sequentially and trying to get the transform at the output.
Yeah,
And
because they're
that is
connected.
variable.
Like there's all these swap gates, the control gates. So if you focus
Correct.
just like in the upper right hand, that Q sphere.
So these are all the swap gates. 1,
Yeah.
2, 3, 4. These are, so what it is doing is it is swapping the the qubits across. So we have swapped everything, and then that is what we get. And now we are trying to do a Hadamard and S gate, and see these are S are the quarter turns.
Well, I
So-
would say this is probably the first time a lot of us have seen this, as far as, you know, like imagining that circuits just go left to right, like this layer to this layer to that layer vertically. And then this seems to be a different approach.
Yes, this is a different. That's why I said no. I was really amazed that we talk so much about Quiskit, but this is much easier because it is available on the web, and you don't need to do much. You just need to. And these NASA folks have been doing it. This is my 3rd time I am attending their tutorial, and I was puzzled that I missed the last 2 times. Is it new? I didn't ask, but I think this is new to me.
Yeah,
And quite of having done
also,
so much.
with a lot of these, keep in mind there's more than one, you know, of different algorithm types. I would
Correct.
assume this is more towards hardware, because typically you
Correct.
have to do all these swap gates, to
Correct.
minimize the effects of noise.
Yeah. So what I will say is here, this is a gate quantum. This has nothing to do with adiabatic and all this, which are not there. So energy, even though I dropped in there, the QAOA and what is that, other algorithms which are annealing based and all, I have not included anything of that. This is simply gate quantum. In gate quantum, we need to simulate, or we have to use the backend. But this simulation appears to be 12 qubit is good enough for most of the theoretical applications we do, which is not industry quality, but at least we are able to do growers. Then we can do what you call the various other algorithms and quantum Fourier transform and shores. So growers and shores are the most important ones, but shores also uses the quantum Fourier transform QFT, and growers is classical plus combination. This is also classical plus combination. Bell inequality is our CHSH, which is nothing but your EPR or whatever we call the entanglement stuff. And entanglement portation, teleportation is here. So you got some real good ones. And all of this, you can save your own, you can make your own version, save it and demonstrate it. So I think this is a cool stuff. Yeah, error control is not here. I will see if there is any way to have error control based on what. So I don't have an answer to that right now, but we'll figure out. Error control, we will discuss next time. And also some of the gates, if any one of you can demonstrate from these any gates, which is just by putting something and then getting out, or even using the existing one, I would love to see participation from you folks who can do something, and then we can talk about the error. Obviously, there is unlimited possibility, but we may have 2 more maximum lectures to clear. At least the exercises I can provide so that you can do those exercises and get certified, at least to the extent that we can expose our people here to be able to leverage on top of it and really do some actual work in the industry. I hope, I think I will end the class today. I do apologize. I struggle trying to get the, what you call the, getting up my, I think I'm going to announce next week on a different, what you call, not on this Zoom, but on a separate, what you call a Geo or something, which I have been using for another one. Monday night I have around 18 I finished and recorded. Here I am not sure whether I am getting recorded or not. I hope I'll get the recording out, but still what I'll do, if I need to re-record, I'll do it, but I'm going to next time change the trying to struggle with this one is not a good idea. You need to have proper this one to be able to close it properly. So last two ones we'll do it on Geo. I'll change the link on the whatever the meetup group and also send you all of you the Geo. Make sure that you are RSVPing on that, so then you will not miss it. But I'll take two more to close this in next 2 weeks to Saturday, to be able to bring you to a level where you can really start leveraging. And as a group, we can build more and more algorithms, more and more error correction, and more gate-based is what is our target mostly. But I don't mind if somebody is able to do QAOA, which is nothing that can quantum advantage, optimization algorithms, QAOA, and those kinds of things. So the algorithms is the key. And obviously we need something to be able to, and this appears to be a good vehicle for at least even assuming that it's a simulation, it is much faster and better. It is online, on the spot, you can see what's happening. Okay. Thanks, John, all of you, and especially for all your comments and for all your patience. And I think Kevin has been very helpful, and John has also joined these days. I didn't see what do you call one more person. What was his name? I forget. He's also very active in this, and so active participation is important to be able to really gain out of it. So I hope we have next week 10 o'clock Saturday. This next time, because I came back from Seattle, just I had to do a rapid study. I was not able to do just.
How was the IEEE stuff?
Oh, IEEE stuff was great. So the new thing that has come is the Microsoft has if on Thursday morning they released their roadmap. Okay, so we do have a roadmap from IBM, we have from Google, now we have from Amazon. Sorry, not Amazon, the Microsoft. They called it the iPhone movement, and they are going to go with the topological quantum.
Okay.
And they have topological quantum. They have shown that they have their own targets, like you need to have 1,000,000 and 1,000. And
what were the qubits as far as their forecast?
Yeah. So their base is topological quantum, and they are saying that they should be able to today get into thousands, and then in a couple of years you'll be able to go to millions. And they have a better story than IBM, so they are contesting now. So the competition is heating up. So it's good.
Right.
And not only that, a lot of tools have come. Okay, like this funny tool came in, right? Many things are happening, and I attended also standards. So we are also getting a quantum standards now. Okay.
Yeah, through IEEE, correct? I thought they already had like 10.
Yeah. No, it's not just IEEE. IEEE is just trying to put more and more of in the hardware, because that is where IEEE scores. But there are standards even for architecture, algorithm. This is all coming out of ISO. So ISO is the top gun. And then it is following by HC and all the European.
They already published some for cybersecurity, at least one of those.
Yeah, so security is the low-hanging fruit. Okay, quantum key distribution is the low-hanging fruit. That's why I said Y2Q is the way to make money if you are looking for a commercial entry. Because Y2Q is like Y2K. Year 2000, they said that everything will break, right? But nothing broke, but everybody made money in that.
So what's the one for quantum?
So for the quantum, the government is going to mandate all the infrastructure providers in the government, including all the labs, and everybody must have a key which is higher than current key. So when you do SSH, what we use currently 256K 2024 max, right? But those are all classical, that is based on RSA and all, right? Public key with the public and private key and all that. The key lengths have to be changed now. Otherwise, quantum will break it.
Right.
because they can compute faster than if you have your P and Q keys, which is going to be the public and the private key, and you are only giving public key. Now using your public key, if they can detect your private key with some kind of a prime number factorization using Shor's in let's say microsecond, and then you are dead. All your information will be, and not only that, they are harvesting. What harvesting means is whatever you do today, all will be recorded and kept in a place, and tomorrow they will figure out what was your
Right. Yeah.
and then take out all your secrets. So all the national governments are afraid of these Shor's cracking. So Shor's algorithm is a big win for quantum.
Yeah, a lot of these things are still way out. I mean, IonQ.
No, they
I
are
think
way out, but you can store the record and get the secrets, right?
Yeah, I mean, for hardware though, for like, so IonQ said, CEO said like, we expect to have like a chat GPT of quantum computing, and then he clarified himself and he said like 65 qubits for ion trap, which is arguably, one of the leading hardware architectures. So I try to keep an eye on the hardware stuff. Did anybody mention anything about noise, quantum noise, and say the Microsoft, for instance?
Plenty of them. I'll share with you.
Significantly lower, like, because I think it's like an Avogadro's amount of more quantum noise than just running on a classical computer.
So that is why the noise is measured in terms of so signal to noise ratio we know in analog, but here they are trying to use a term fidelity, and that fidelity is 99%. They
right,
want
like if you hop on
99.99.
a Qiskit, like for single gate or double gates, like for a single gate, I think it's 10 to the -4, but I think it has to go all the way, like say classical might be
7,
negative
10 to the 7 or something. Yeah.
for classical.
So what we are seeing is 10 to the power -7 to 10 to the power -9 is the target.
Is the target. But,
correct.
Like to do anything like sensitive data, like anything with quantum, you can't have noise. So, so designing models and running big,
that is the reason everything is designed on terms of CC naughts or Clifford T, right? Universal. So you limit yourself to the gates that you can operate at 2 or 3 qubits, and that means you are minimizing the errors in a given operation. And when you have depth and width, that is of the circuits that determine to make sure that's why today we are limited to maybe they are saying 60 operations. 60, that means what? If you have 3 blocks, each block having 20 gates, at the most you can do 60 depth.
Yeah.
So if you try to go beyond 60, the errors creep in and you're not able to manage, and there is no. So that means computers are not ready.
Like what you're saying, 10 to the -7, something like that for a single big problem. Correct. That makes sense. It's not anywhere close, because in quantum machine learning, you have to do all these mini batches, say like 10 mini batches per epoch. And then if you have, probabilities with quantum noise, whereas we can get exact solutions through simulators without any quantum noise. So yeah, it's just, as far as workflows, I don't think, as far as the effort goes behind these press releases and people up on stage with hardware, it's just for big problems, which is good. But if the primary application is QML, why isn't more of the attention placed in quantum inspired? It doesn't make sense.
No, quantum, there will be different voices from different people in different directions. The chemical guy will only talk about, I am fermion and boson. Fermion electron is a fermion type and boson is photon type. So I have only 2 types and I am more interested in this. Can't do anything about it. Same way, operation research will come and say, hey, I am more interested in the operation research. I'm not going to use your gate computer. I am better off with QAOA algorithm.
Right. Okay. And it's not nearly as like cool to talk about quantum noise as it is number of qubits, but in headlines and everything, it confuses the heck out of people, because they say like, we have a 400 qubit, we plan on 1,000 qubits by, I don't know, 26.
Yeah, so one approach.
There's so much noise that it doesn't really matter. right? Like as far as like, you know, typical workflows that
Yeah,
how we
this is
see.
like
Right.
everybody wants that I am the supreme, right? Quantum supremacy, everybody wants to claim, whether it is China, India, US, or even corporations like IBM or Google or Microsoft. Everybody wants to claim that they are the supreme, and they are all of them. What are they trying to do? Attract talents and put people in their group so that they can succeed. Everybody wants to succeed, right?
There's the Penny Lane demo on this, and
Yeah,
it takes,
Pennyline is also there. That is part of the QML.
yeah, well, it takes the circ.q sim that was used against the quantum advantage, the real hardware, and it cuts
Yeah.
the number of qubits, I think, to like 16 instead of like 50 something, because
Yeah.
they ran that simulator on a real, you know, supercomputer, and now we're running it on like a Xeon processor. But it's missing a lot of information, because like you can get the speed in a certain specific fashion, and I think that's what quantum supremacy was back in, you know, 2019. But the other metrics like accuracy, loss, those types of things, I don't think that you can get that, right? So it's just, if you open up that, it's a Penny Lane, it's called I think it's quantum and advantage, something like that.
Yeah.
So it's Google's
See,
QSIM.
the term is quantum advantage.
But if big
Optimization
hardware can get a big, you know, a big problem with, like you said, noise like -7, I think that'll be like a breakthrough for that, because that's something we've never seen. We've never seen a huge problem, you know, with quantum.
So
Even if
there are
we have
many researchers focused on this, and it has really produced a lot of things. In fact, the Sycamore Google, what they have done, they have shown their circuits, they have exposed their circuits outside, saying that this is what we did, and still we are falling short. Everybody is falling short because it's not an easy thing to do. Whether you do simulation, after simulation, when you come to hardware, you are going to get bogged down because you have a physical, right? And physical can be anything. It can be, the newest one is what, they want to do everything at this room temperature. And for that, they have got a NV, that is a nitrogen vacancy. That's a new technology people are chasing now.
Well, I think for big hardware, it's less about like trying to run it inside applications, and just what is the core technology. And this is not like favoring any one of them, that can get its error rates down and keeps getting its error rates down, because that'll be the end problem. It'll be stuck to very limited, you know, problems if the error rates are so high.
No,
That's correct. And the programming won't matter at this point.
Everybody is trying to get their error rates. See, normally what we say in if you're a communication guy, you will say, "Hey, I have 1,000 dB. That means I 3 dB. So 30 dB means I have 1,000, right?" So that is the way we look at signal to noise ratio there in a communication channel, right? Now, these are quantum, and these are nothing but individual quantum qubits. They are not even connected to each other, but they are close to each other enough that they will interfere. A crosstalk will be there. So the physical deployment is challenging, because even if you talk of a semiconductor or why are we doing it superconducting temperatures? Because your thermal noise is reduced to zero, right? Almost. And that's the reason you do superconducting. But the circuits don't operate there. So you have to create specific circuits which can be used. And that is where the millikelvin and Kelvin temperature. So they have elevated the control portion, because at the end of the day, if you do a superconducting or you do a photon and all this, you are using frequencies and you are using pulses. And so if you give a pulse, and there in quantum, there is no, what do you call, quantums are all combinatorial. There is no sequential timing based, clock based. There is no clock here. You don't do at a clock leading edge like we do in normal electronics. Here, everything is combinatorial. So you have to take a shot at it, try one and measure it, try one and measure it. And when you measure, you lose. So
when we go to it's kind of like fiber, the transceivers in fiber, because you're trying to set this up with the electronics, basically transfers an electronic signal into a light signal, and then that pulse is picked up by the other side. That's what I'm kind of figuring out what they're doing in the middle of this.
Yeah, no. So when you talk about the photon based, sure, it can be using but then they are now talking about intermingling, that is interoperating between a photon and an electron spin based as well as superconducting quantum based. So there are no interfaces that can be, they are not standardized yet. And each one can have their own, but then they cannot interoperate. Like we did in hybrid cloud, the same thing is going to happen here. So essentially, it will take some time, but slowly and steadily over a period of next 5 to 10 years. So the career opportunities in this is next 10 years, definitely more than 10, because then it will last to maintain that. So at
Well,
least 20 years.
I don't know, like as far as a big problem, I see it before that, but something that's like, more functional across several different data sets, these types of things. I don't think it'll be that long for a big problem for hardware.
No, hardware is the blocker right now. Simulation is the way to overcome emulation, and then finally it will go to real embedded circuits. It could be in FPGAs, it could be in big what do you call the data centers of the world. It will be over the cloud for time sharing and all that.
Well,
So-
Dell is already using emulators, IMQ's emulators. It wasn't huge news, but their, business, their enterprise suite is, they're emulating, I think 32 qubit, circuits on classical hardware, that are quantum algorithms.
So ion trap, see, ion trap is what the IonQ is promoting, right? So you trap the ion in a cavity, which is a semiconductor cavity, and then you have the what do you call the tunneling, which is happening by improving the energy level on that, or by creating vacancies or whatever. So instead of the avalanche where we try to overcome in semiconductor phenomena is also a quantum phenomena, but that's not quantum computer. That is still doing binary, but it's not doing the state-based implementation. So even though semiconductor phenomena itself is a quantum phenomena, but it's not quantum computer. Quantum computer is one where you are able to manage the state transitions and apply the algorithms to get the advantage over the classical bit-based. This is two level instead of two level, which is 0 and 1. Here we have multi-level, and you superpose what n number of qubits, so you can do one shot all the operation. You may repeat it a few times just to get the how many times you want to take the how much a shot should contain. 24 attempts or just the 10 attempts, that also is debatable right now. Ultimately, how much, because it's approximation computing, right? It is not a exact, but you can get to the exact, or you can leave it at approximate and go ahead with the results and then conclude and be able to use some other methods to get there.
Yeah, I
So,
mean, that's just hardware.
Challenges are there. Challenges are there on the error side of fidelity side of it, performance benchmarking side of it.
We can get the exact answer for ML workflows right away. So we don't have to, like, that's the nature of quantum computers, is reversible. You need to take a bunch of shots. I don't know if it'll ever get to the point like a classical computer where you can just output. But there was actually an example of this in Penny Lane in their documentations. The number of shots saved to the real answer to this Hadamard circuit was 0, and the simulator returned 0 right away. It took like 100,000 shots to not even get 0. So it was like 0.000, I think it's like 4 or 5 zeros. And then, so yeah, different technologies, but you have to consider all these things, because people want it now. And like the Wall Street paper this week is big because it mentioned sandbox AQs, and I think Terra Quantum as well. They're big into, quantum inspired, and they could do it now. It's basically, you can run quantum circuits without the limitations of the hardware based on technology that's, classical technology that's advanced.
So, Kevin, if you can demonstrate Penny Lane, that will be super if you can. For
level. I mean, for this group, I could do. I've done presentations. I broke down the 10 steps in the raw documentation. That's not as flashy as the next one I did, which is 26 of their QML demos, either improved, mostly improved, or modified. So, It's for me, it's spur of the moment. So if there's extra time, to do these types of things, I could potentially do that.
Yeah, even if you have presented earlier, you can present it same thing sometime. I will ask Taposh to organize one of the days.
Another one I
So
did.
whenever you are ready, okay, whenever you
Yeah.
feel comfortable.
Yeah, I did Qiskit versus Circ versus Penny Lane. So those that are never going to go to Penny Lane and are interested in Qiskit, it breaks it down, like trying to keep it the same as far as like this specific slide. Here's the code to set it up for, training circuits and machine learning, where this is the code. And I'll provide examples how to print the circuits for each of the three.
Mhm.
So that's another one too. So
Yeah. Choose your time of when you can do it. But what we'll do is we'll take two more on this using this whatever new discovered tool, and hopefully algorithm portion, circuit portion also I'll show. But we can have some questions and all, which I'll send to everybody. If you can solve that, then we have at least one way to cover what we have started and be able to leverage on it. And as a team, a lot of people are there. I'm pretty sure we can move forward to the next level.
Yeah, and a number of us, I think, have done the Qiskit Composer. If you could say,
Correct.
and I know in this one, instead of 0, you can select it on that left tick. It's like 1 or minus or plus.
Mhm.
I didn't see that in Qiskit right away. And then you can also do anti controls. So instead of the solid dot, it's a hollow dot. And I've seen that in literature. I just didn't know what it meant.
Mhm. Yeah, it's a good tool to look at and learn, because if you have multiple tools capability, that will help you. Certain things are solved better with something than the other, and algorithms are all over the places. And it is whether it is a what you call the simulation or twins, creating of the twins, or creating of the searches, or the creating of the subject matter specific, like physics or operation research or chemical, or we don't know which industry demands what. But having to know all that, even at the surface level, knowing what is right is itself a big deal at this time.
And fully studying one and figuring it out. So say for like I think it was the QFT, how it goes down with time. I mean, that's look to me, because most time series goes left to right, but this is going top to bottom, like how it's doing in your background right now.
Yeah. So what is happening, the challenge here is understanding what is QFT, right? And then how is it being applied by as a subroutine by other, like Shor's algorithm uses QFT as a way to select the prime, right? Because there is a periodicity. So if I do a multiplication of prime numbers, there is a periodicity which is happening in the trying to get to the prime number when you do a modulo numbers there. So then that periodicity is determined by QFT, obviously. So Shor's is using QFT as a subroutine. Search similarly can use something else as a subroutine. So you got bunch of subroutines, oracles created, and it's like a what you call controls, which you used to call in the case of Microsoft. They say, oh, you got controls, you have to drag drop the controls. Similar drag drop will come more and more. It will become prominent. It will become an easy approach to everybody. And instead of worrying about the qubits, people will start worrying about the application. Then that's what we want. But then error removal, error feasibility, the performance, the clops and the RQ lops, something they call it. Everybody comes up with the new terms.
Yeah.
That is,
I mean, if you had
layer operations, there is clock.
Like Aram Haro or Seth Lloyd at MIT, for instance, they could say why exactly each of these gates were placed here. It's a hard place to get to, but it helps because it helps to understand, and even when you're doing broad ML stuff, and how quantum computers do quantum circuits.
Okay, Kevin, I think it's time to close for today. I enjoyed all people, and hopefully next 2 weeks we will try to wrap up by at least getting us to a level where we can do some design, some deployment, and some demonstrations. And within our group also, whoever is willing to present, the floor will open after 2 weeks to everybody. Each one can present their cases, what they are working on, and that way we can learn from each other and move on. Okay.
Awesome. Yeah, appreciate it. Have a
Thanks
good weekend,
everyone,
everybody.
and I'm going to